Hi and welcome back to Properties and Structure of Matter, and we are looking at an inquiry question 4 all about bonding. Today we're looking at the shape of molecules. Now, in our last video we were looking at the difference between polar bonds and polar molecules, and we talked about our polar bonds when the difference in electronegativity between the two atoms is greater probably than about 0.4. One of them has a greater electroaffinity or electronegativity for those electrons there and have a greater pull, and so the electrons spend a greater portion of time around that electron, creating a slight negative charge there, and we call that a dipole. So our molecule, if we talk about it in terms of a molecule, our molecules are considered non-polar if the sum of the bonds dipoles are 0. So if the dipole positive, dipole negative, if they're different, if they're non-zero, then it is a polar bond. If they are 0 and cancel each other out, then it is non-polar. So this leads us in then to the shape of our molecules. So the shape of a molecule helps determine some of the physical properties of the covalent bonds, the covalent substances rather, and their shape can affect a variety of their physical properties such as melting point, boiling point, hardness, solubility, and so forth, because the shape it actually has determines how is it going to react with other things. So how does this happen? We have something called the VSEPR theory, which is the valence shell electron pair repulsion theory. Sounds like a bit of a mouthful, but it's really not that difficult. And there is a little link there to a video that is quite good to help you if you need some extra help. But we'll go through some of these shapes today, and we'll also look in class and work with some modelling and our MollyMod kits to make this a lot clearer. But basically our VSEPR theory is based on the principle that if I've got all these electron pairs around my atom and electrons are negatively charged, then they're going to repel each other. So when they're all repelling each other, they're wanting to move as far away from each other as they can. So how does this work? So all our atoms in our covalent molecules, as we've said before, are most stable when they have 8 electrons, and we call this the octet rule. And when you might have seen in our Lewis structures, we arrange those electrons into pairs. So they are electron pairs, 2 together all the way around. So not all electron pairs will actually bond. We have things called lone pair of electrons, and again you will see some of these. But they're treated the same as a bonding pair when determining the shape, because they are still having a negative charge and therefore still repelling the others. So how do we determine the shape of this molecule? So Lewis structures just give us a 2D view. As you can see in our picture here, it's 2D, gives us no idea about the structure, or rather the 3D shape at all. So the Lewis structure here, we look and we go, oh, okay, they're all 90 degrees, but in actual fact, it has a very different shape. So let's have a look. Say, for example, methane. Again, the similar 90-degree angle. You might think, okay, well, how can they get any further apart? But we're looking in just a 2-dimensional shape. But if we imagine the 3rd dimension, the hydrogens can actually get further away. And again, with our modelling practice, you will see that this is the case. When we take that 3rd dimension in, it'll actually allow for about 109 degrees between each of those, and that way then we're reducing the repulsions. So we have 5 main shapes. Yes, you need to know them. 1 is our linear. So it is when we just have one central atom with 2 on either side, and they are 180 degrees apart. They can't get any further. If they were slightly bent, they'd be closer, and if they were bent the other way, they'd be closer. So linear is the best way to go. Trigonal planar is when they are actually all within the one plane. Again, when we model these, it'll make it a lot more sense. But you can see with the balloons above, they are all in the same plane. And they have 120 degrees between them. Then we have our tetrahedral shape, like we used in the example previously, and you can see that there are 3 atoms in one plane and then the 4th one above, and electrons, not atoms, I mean. Then we have our trigonal bipyramidal, so obviously there's more, and so we've got coming above and below, and our octahedral. So how do we go from the Lewis diagram to a 3D shape? So we start with our Lewis structure. So we count the amount of electron domains. What are electron domains? Electron domains are every single, double or triple bond counts as one domain. And each lone pair counts as one domain. So basically we're looking where all those electrons are. Then we're going to use our chart to determine, based on how many bonding and non-bonding domains there are, will help us determine our shape. So let's have a look. Here we have a bit of an example of what we mean by lone pairs and what we mean by bonding pairs. So if I have these ones here are bonding, okay, because they're bonding to another hydrogen. Here, these are in pairs, but they're not bonding to anything else. So they're considered lone pairs and they're non-bonding. The 2 down the bottom are bonding. So let's have a look at this atom here. We've got a carbon central atom. We've got 3 hydrogens around the bottom, a fluorine at the top. How many is there? Every bond is a domain. So in this case, there are 4 domains. In the case of a boron, again, 1, 2, and 3 domains. Carbon, 1 and 2. Doesn't matter if it's single, double, or triple bond, it is considered one domain. So looking again, have a look at these. Again, it is repetitive. Okay, now this one's a bit tricky. One domain, but here is our electron lone pair. So it counts as a 3rd. Same here. 1, 2, 3, lone pair, 4. So our electron domains are all negatively charged. They want to spread out as far enough away as possible, as they can, and that allows it to be much more stable. So let's look at some examples quickly. How many bonding and non-bonding are there? 2 bonding, 0 non-bonding. So what's that mean? So using the VSEPR, we're going to see that they're arranged around the central atom. The best way that we can get them is that they are linear. So they are in a linear form. This one here, we have 3 bonding electron domains, no non-bonding, so they're all spread evenly around, so they're going to form our trigonal planar. Looking at this one, we have got 4 bonding and no non-bonding, so again they're going to form our tetrahedral shape, which is 3 in the one plane and coming up out in the 3D shape. Now this one's a bit different. We have got the 3 here, but we've got the lone electron pair, or the non-bonding pair there. So what are we going to get? Basically, there is no bond coming up to another atom, but those electrons are still there pushing away those other electrons. So the base shape will stay the same. So instead of being that tetrahedral with the bit coming up the top, that's going to be just 2 electrons there because it's not going to another atom, but the bottom shape will stay the same, and so it will form a trigonal pyramid. And looking at this example here, again, 2 bonding pairs here and here, but we have the 2 lone pairs there. So what's that going to do to our shape? Right, so we've got the 4 all around, but in this case here, we get a bent shape. So what's going to happen is that's why we get our typical bent sort of shape there, because we've got the 2 electrons around, and so we have to have the same gap between each of them. So while they have the same angle between them, we're not seeing those as bonds. So what we see when we draw it is just those bent shapes there. Oops. So here you can see they're almost all the same. They're all the tetrahedral shape. We've got the 4 technically 4 and technically 4 different pairs of electrons there, but the difference is not all of them are bonded to something else. So we can see in this one here, we do have the 4 bonds. Here we've got the 3 down the bottom, and these do not bond to anything, it's just a lone pair. Here they are still there pushing the other angles, the other atoms away, so these have got that bent shape and these ones are coming up there. Lots of practice ahead. See you soon.